Hi everyone, welcome to another MATLAB live stream. We are live from the Lakeside campus of Mathworks, which is in Natick, and it's just west of Boston. Thank you so much for joining us. We're going to get started here really shortly.
Yeah, I think it should be an exciting next hour or so. This should be an interactive session, so please feel free to comment and ask questions in the chat.
Yeah.
We're going to try to get to those as we progress through the demos. Why don't we start by introducing ourselves?
We should probably do that. My name is Akash Gopisetti. I am a product manager here at the Mathworks. I work with the Simulink and signal processing teams. I've actually had several roles at Mathworks. I joined first in the engineering development group, and then I worked in the education marketing team, where we were promoting STEM education at high schools and middle schools, which is really cool. Actually, Mathworks has a lot of active investments in just STEM education programs for students and teachers across the world, which is really neat. But yeah, and then I moved to this role where I am right now.
Very cool.
Adam?
Yeah, and my name's Adam Cook. I'm in the applications engineering group here at Mathworks. That basically means I work with our customers and help them use our tools to design their products. And the specific tools that I focus on are signal processing and audio-related tools, and those are the things we're going to be talking about here today, and talking about Simulink and a smart speaker model.
Yeah. So yeah, we're going to be talking about just signal processing in Simulink. So if you're new to signal processing, or if you're new to MATLAB or Simulink, this should be interesting for you.
Yeah, definitely. So let's go ahead and take a look at the model that we're going to be showing you guys today and give you a quick introduction and just kind of give you the lay of the land, and then we'll start going basically through all the different components of this model, do a detailed deep dive on all the different parts.
Yeah, and the cool thing about the model today is it just has these different components all mixed together.
Yep.
Right? Like, what are we looking at here?
Yeah, so the smart speakers is a nice demo of what we can do in Simulink for audio and signal processing, because it's got, so much going on kind of all at once. We've got audio input processing happening up here in the top rectangle, output processing happening down here, and we've got our devices and scopes over here. So why don't I go ahead and just quickly show you what the model can do while it's running. Then, like I said, we'll go ahead and dive deeper into each section a little bit later on.
Sure.
So I'm going to unpause the model. It's currently in a pause state. And then I'm going to flip over this switch over here, which is going to give the model a go command. And because the model has speech recognition built in, so when it hears the word go, it's going to start playing back some audio, and we should hear that. And then I'll just flip around a few other commands so we can see what else it can do while it's running. All right, so now the model's in a running state. Whoops, I had saved it in a pause state for too long, so let's go ahead and start it back up again.
And I should say this is the Simulink environment that we're looking at, which is a visual platform, and it's really good for simulating and modeling dynamic systems. So yeah, this is the Simulink platform.
Yeah, thanks for those basic fundamentals, which I skipped over. So the model is now running. You can see that indication down here by the T representing our time is increasing. Mm-hmm. If I go ahead and flip over the switch, as I said, over to go, then we start getting audio playback. And we can hear that playing back, and we can also visualize it using these things we call scopes up here. We have a time scope, which shows the time domain, and we have a spectrum down here, which shows the spectral domain. So that's the model in a nutshell.
Yeah. So I was talking about Simulink earlier, and I like asking this question to people, but just speaking of Simulink, when did you first hear about Simulink or start using Simulink?
Yeah, good question. So I used MATLAB first, probably like most people, but Simulink I discovered a little later on is a really cool tool that builds on top of MATLAB for doing this kind of graphical style programming.
Yeah.
And I see it used quite a bit. Like I said, I kind of came from the audio signal processing industry before I joined Mathworks, and I see it used as a tool there for, developing algorithms. It's really nice tool for quickly testing and prototyping different types of of new designs and algorithms, and then you can take those individual components and individual algorithms, and you can assemble them into bigger overall systems, like we're seeing here with this smart speaker example.
Yeah, yeah. Okay. So should we just go through what this model is doing? I know we're modeling a smart speaker.
Yeah.
And actually, fun fact, about 43 million Americans have smart speakers in their homes, which is, I think it's like 18% of the US adult population. I was doing a little bit of research for this.
I see. Yeah. There must be a lot of smart speakers listening in on everybody around the world, I guess.
Right. Yeah, I feel like in the future, everything's just going to be smart speakers everywhere, which is really cool.
Cool and scary.
And scary, yeah. So right now we have a version of a smart speaker.
Yeah.
Actually, another trivia, the first digital speech recognition tool, so not quite a smart speaker, but something that could tell words apart, was actually invented in 1961.
Oh, wow.
And it could tell apart 16 words.
That's pretty good.
Which is just insane. Because 1961, we had the remote control coming in. I know what else we had. Star Trek came in.
Yeah. I didn't know there was smart anything back then.
Yeah.
So that's pretty cool.
All right, Adam, so what are we looking at here? Should we dive into the model a little bit?
Yeah, let's do that. So we'll kind of go through each section, and then as we kind of work our way, we'll kind of work our way starting in the top left in this audio input path, and we can describe each of the different blocks and components. And again, feel free to ask questions as we go through, and we show you these different things.
Yeah.
So let's start up here, zoom in a little bit. And so as you can see, this is the audio input path. And what we're modeling here is a voice command that's coming into a microphone array, represented by this circular ring of dots here. Each one of these is a microphone in our kind of virtual model. And this allows us to test out the quality of a particular microphone configuration. Some people, they might have the flexibility of choosing how their microphones are going to be placed, but more often than not, these sorts of microphone placement decisions are made for aesthetic reasons. The product designer says, oh, it has to look like this and it has to have this certain size.
Yeah.
So the person doing the microphone array design kind of has to conform to a certain geometry, so to speak, and then make their microphone array work as well as it possibly can within that geometry. So this circular geometry is a common one that you see on devices. You might have noticed that many of these devices happen to be circular.
Yeah.
So that's what we've modeled here to kind of represent that fairly accurately. And what's cool, if we dig into this, each one of these blocks actually has kind of its own system underneath. So I can click this little down arrow here and look underneath, and I can see all the stuff that's happening in this block. And it's a combination of the microphones themselves, as well as a beamforming algorithm. So,
Right.
You familiar with beamforming?
Yeah, I was going to ask you, what is beamforming?
Yeah, great question. So it's kind of exactly what it sounds like. It's the idea of, can we acoustically steer a beam in a certain direction? And the reason we want to do that in a smart speaker is, to maximize the quality of the recorded audio, when you're talking to it. I mean, so where would you typically place a smart speaker, right? Where would you put it in your house, maybe?
Right. It could be at the, the living room, next to the kitchen where I'm cooking, or the bedroom. Yeah.
Right. So a lot of us will place these things in parts of our house where there could be a lot of other noise going on, like especially in the kitchen.
Right.
So the smart speaker is always listening, and when it detects voice, there's usually an algorithm. We haven't actually modeled that part here yet. Maybe we'll get to that. That will actually detect where the voice is coming from.
Right.
And then attempt to steer the microphone beam in the direction of the voice so that it reduces the sound of the washing machine or the, the person washing dishes or the person vacuuming or whatever else is going on in your house.
Right. Yeah. So you're sort of focusing the beam to a particular direction.
exactly, exactly.
And that probably just minimizes power consumption too, or optimizes power consumption, just because you're not listening to everything, you're just listening in a particular direction, right?
Yeah, so it's about maximizing, they use the term signal to noise ratio in kind of the audio DSP area. Yep.
Yeah.
Actually, question.
Yeah, there's a question. Let's get that one.
All right.
So the question is, can Simulink use my mic as the input of the data and analyze it in the time frequency domain?
That's a great question. So yes, the short answer is yes. So here, what's cool about this model, I was just describing kind of the simulated input path where we actually play audio files into this simulated acoustic beamformer. But we could also use a real microphone. And I have a switch down here that allows me to control that. So when it's in the up path, it's taking the signal from the simulated path. And when it's in the down setting, it's taking the signal from a real live microphone. So let's test that out, because I think before when I showed this, I was using the simulated path.
Right.
Go.
Cool.
And stop. All right.
Nice.
So as you can see right there, I gave it the two different commands, go and stop, to start the music playback. And we had the live real-time visualizations over here showing the time audio and the spectrum analyzer audio coming in as well. And actually, I was actually demonstrating the audio that was showing on these scopes was the playback audio, so the guitar audio that you heard playing back. But I could also show the microphone audio if I wanted to, so it's up to me what I want to show in those scopes.
Yeah, and I guess since we're talking about it, the audio device reader block, so that's basically picking up audio from your microphone, right? And you can configure it to pick up audio from different sources.
Yep, great point. So this is a block that comes from one of our toolboxes we call the audio toolbox. And it basically talks to your sound card, right? So on my laptop, that's the microphone that's built in. But it could also be a external audio device that you've hooked up to your laptop, such as in a laboratory, you might have a more expensive interface for like measurements and things like that. So we can support all those kinds of things. This is probably a good time to show them some documentation too, right? We haven't done that yet.
Yeah, sure.
Maybe I'll pull open the help page for this audio device reader.
Yeah, and that's the cool thing about Simulink is you can just sort of right-click a block like Adam just did that, and then scroll down to like the help section and then pull up the documentation. And that just gives you all the information that you need to use that block in the model. So that's what we're looking at right now.
Yep. So this block diagram kind of represents what's happening inside MATLAB or Simulink when you use this audio device reader, and shows how the audio data streams into the application. And then another thing we could highlight in the documentation area is actually, we forgot to mention this at the top, but the smart speaker that we're showing you is, this example just lives within the product. So you could search for it in our documentation, or you could even just go to like the Mathworks homepage and search smart speaker. And you're going to get the model smart speaker in Simulink right there. So this is the same thing that shows up in the documentation, is available on the web as well. So
yeah, so you can actually go to this page or this link and look at the model that we're talking about today and follow along, or pull it up in MATLAB and Simulink if you wanted to try it.
Yep, I think we're going to share that for them in the chat as well. So
yeah,
you'll be able to have that link there.
Great. All right, so we talked about the acoustic beamformer, and we talked about the mic input and the simulated voice input. Should we go on to the next block? I guess that is the AEC.
Yeah, let's do that. Actually, I thought of one other thing
Yeah.
I think would be cool to show with the beamforming. We talked about what it does, but I think it'd be cool to visualize it. So let's do that. So we're showing Simulink here, but as we talked about, Simulink lives on top of MATLAB, and we can use MATLAB as a handy tool for analysis of the things that are happening inside of our Simulink model. So what I have here is some MATLAB code that actually analyzes that microphone array and plots the response of the beamformer. So if we look at these three different figures here, on the left-hand side, this is the same thing that we just saw inside our model. So it's that circular array geometry.
That's the orientation of the mics, right? The microphones.
And then we talked about beamforming. So here's kind of literally what that looks like in 3 dimensions. So right now you can see you kind of get this blob shape, and what that represents is when you steer the microphone in a certain direction, you can see that a certain portion of the blob is kind of stronger. It's kind of pointed in a certain direction. That's your beam basically, and then there's less signal in other directions. So in this case, you could either look at it in 3 dimensions or in 2 dimensions. And when you look at the 2-dimensional, it's a little easier to see that the beam is actually steered right now at 30 degrees. So we could move that around by basically adding different beamforming weights to the array geometry. But right now we've just decided to steer it to 30 degrees. So this is a cool tool that we have in MATLAB for analyzing these beam shapes.
Yeah.
See, we got another question.
We do. Okay, so the question is, how do I extract features from my signal to train my machine learning model?
Okay, that's a good one.
Yeah.
So why don't we jump around in the model a little bit based on these questions?
Sure, yeah.
We'll come back to some of the blocks that I skipped over.
Let's do that.
But I think, so that question is related to our speech command recognition, right? So we talked earlier about how the machine learning portion of this model is doing the speech command recognition.
Right.
And yeah, extracting features is a big part of training a machine learning model. So let's look inside this block, see what's going on under the hood. We've got, from left to right, a few different interesting blocks. We have this thing called auditory spectrogram, and this is basically the features that are being passed into my machine learning model.
Right.
And that model here lives inside this block that we call predict, because it's already been trained at this point. So now it's just doing new predictions on audio data as I pass them in.
Yeah.
So to answer the question, before we could get this trained model into Simulink, we had to do the training. So that means that we had to extract features inside of MATLAB and train a model. So yeah, so we can go back to our documentation again and show you the example that actually does the training of that model. So I think if we search train speech command, I think it'll come up. And there it is. And here's another example that maybe we could share in the chat, share the link for you guys. And the feature extraction that's happening here is pretty near the top of this example, because as the question astutely points out, we have to extract features before we can do training.
Right.
So if I scroll down a little bit, I won't go through every detail of this example, but I will show the step where we do prepare the data for training. Right here is where we extract features. And we use a really cool tool in the audio toolbox called the audio feature extractor to do our feature extraction. That's a
good name.
Yeah, isn't it?
So is this the actual training model that you're using in the Simulink model?
Okay. Yeah, so what we did for our smart speaker was we just took the output of this MATLAB example, which is the trained model, and then we brought it into Simulink inside of that predict block.
Okay.
So, so the model here is being trained on a set of different words. We're not using all those words for our smart speaker. Maybe we will in the future when we want it to do some more things.
Other stuff you can extend.
But right now we're using 4 of the words that were trained from this example.
Yeah.
And yeah, this audio feature extractor, this is a really cool feature because it's super easy to use. We try to set it up so that the most common features that you would use for machine learning are just all available within this one function or this one tool. And in this case, you can actually see here the feature that we're turning on is something called the bark spectrum. So it's basically a spectrogram, which is representing our signal in the time axis on the bottom and the frequency axis going up on the Y.
Yeah.
And then so we can see the change over time on this time frequency representation.
Right, right. So it's a sort of a time frequency analysis of the signal.
Yep. Yep.
And that's a common technique used for transient signals, right? So signals that change quickly over time.
Yeah.
That just reveals information that you would normally just miss out on.
Yeah. Yep. So we can visualize it here, and basically the the machine learning model, whichever one you happen to choose.
Yeah.
I think in this case we might have used a convolutional neural network, but the machine learning model is learning how those features change over time for the different words that we give it. And then it basically is able to match those pictures, so to speak, the spectrogram pictures to the different words.
Yeah.
After you do enough training.
So I have a question here. How accurate is the prediction? Like how?
That's a good question.
Yeah.
So we do have some metrics, I believe, in this example. If we keep scrolling down a little bit, that show the overall accuracy. So we have two ways of looking at it. So one is you can kind of look at the error for the overall training set. In this case, it's a 2.7% error, so it's roughly 97, 98% accurate.
Right.
So that's pretty good.
Okay. Yeah, that's really good.
We do get a little bit higher validation error. That's fairly typical for the validation to be a little bit higher, because the idea is, the validation is data that you didn't use during training. You held it out specifically to kind of validate how well your model trained on the training data.
Yeah.
So it's usually a little bit lower. In this case, 6% error, so it's about 94% accurate on the validation data.
That's pretty good.
Yeah, it's good enough for, like you saw when I gave it the commands, it usually recognized it pretty well.
Right, and then I see the confusion matrix for validation.
Yeah, so this is a deep
that
dive.
looks like a cool graphic.
Yeah, down here we could do a deep dive into the accuracy of the model that we're using in our smart speaker and see exactly which words are, how accurately they're being detected in most cases.
Okay.
And you have to remember also, when this is trained, all these different training, different speakers, different amounts of volume for each speaker, and different noises going on for each speaker. So this is kind of the overall accuracy. Generally, the model is very accurate if you speak clearly and don't have background noise going on. You're probably going to do even better than 95, 96%.
Cool. All right. Should we go back to our model?
Yeah, let's do that, and let's keep going. So the last thing I'll mention here, we just learned about how this was created. Actually, what I can show now is we can rerun the model, and we can, now that we understand what is happening in the prediction block, we can go ahead and start the model again. And I want to show you one other cool visualization that we have available to us when we're running this. So what this visualization does for us is it shows us the network activations inside our speech command recognizer. So by network activations, you can think of it as like, what is the network guessing in terms of the predicted output? So the network's guessing which word is coming in.
Yeah.
And this, on a scale of 0 to 1, is saying, oh, I'm 100% confident it's this word, or I'm 80% confident it's that word. So that's what we're going to be seeing here.
Cool.
And the 4 different words that we're using in the model, you already heard a couple of them. You heard me say go and stop. And then there's 2 other ones. There's down and up for the volume. So let's go ahead and play again. Let me make sure where I left my microphone setting. Okay, so it's using the real-time mic right now. So we could give it some different commands. Go. Up. Down. Down. Stop.
Yeah, that's that 97% accuracy. That's
yeah, so it understands me pretty clearly. I'm kind of used to talking to it, I guess. But you can see like it jumps up to pretty close to 100%. Amplitude of 1 equals 100% confidence that it's hearing you say those particular words.
Yeah.
So that's a neat tool for debugging and visualizing what's happening in the model as it's running. All right, where should we go next?
So I wanted to just quickly stop here for a little bit and just talk about Simulink, right? Because one of the cool features about Simulink is that it's a visual platform. So you can look at the model here and then quickly get a sense of what's happening in it. Because you can like look at, at the left, that's your source blocks, and then it flows into each of these other blocks. And you get a sense of what's happening in the model.
Yep.
And I'm just comparing this in my head to like a block of code, right?
Right.
Where you see a block of code, but it's going to take you some time to figure out what actually is going on. But with Simulink, it's just this visual representation of the system. So it just makes it easier to get a sense of what's happening.
Yeah. Yeah, that's what I like about using Simulink. And like I said, I started off in MATLAB, so I was programming by hand earlier on, and then I moved over to Simulink. And yeah, you're right. Like, this is a good example of the fact that if we were to author this in any programming language, whether it's MATLAB or C or whatever,
right?
We'd probably be looking at thousands of lines of code, in front of us, and a lot of scrolling to try to figure out the system. And here the model is just, it's there. It's all, it's a visual representation, but it's also executable. So we can see what's happening and we can make it happen all within kind of the same model.
Yeah. Okay, so we covered sort of the input branch. Adam, if you want to maximize the model. So just a quick recap of the input branch. So we had the word either simulated or to the microphone.
Yep.
Right? So we had a switch in there to sort of toggle between them. We used the beamforming to sort of look at the microphone array and the beamforming aspect of things. Then we had the AEC block, which we didn't really get into, actually. So we should probably talk about that.
Yeah. Okay.
Yeah.
Let's. I see we have one more question. Let's answer that question, and then we'll come over to that AEC block. So we're similar to the previous question asking about features. This is another really good features-related question. Is there a way to determine which features are most important in classification? Yes, there are some handy tools that we have for understanding which features are most important. There's some ways to do it, more, I would say, like mathematically, but it's also, you might want to just try like an analytical approach, iterate across different features, and we have a really cool tool that helps with that when you're training a model. Let me switch over to MATLAB real quickly and just show you this tool that we have for training models that we call Experiment Manager. So if I go into my machine learning and deep learning apps, there's this tool called Experiment Manager here. And the idea with this is to set up a set of experiments when you're training a model, because we talked about the workflow earlier, but it's always a multi-iteration kind of process, right? You start off with a guess about what features are going to work and what models are going to work.
Right.
But generally, you're going to try out a bunch of different types of features, a bunch of different types of models.
Right.
And you can use the Experiment Manager to drive that.
Yeah.
So let's open up like one of these simple examples here.
Right.
I'm just not sure if we have one that iterates across features. But
Right.
let me.
So I'm thinking once you first get started, you probably have a sense of what features are going to work for you, depending upon what you're trying to get at. But then this tool probably gives you some statistic analysis that you can actually be confident about where you're going with it.
Yeah. So you can sweep across both hyperparameters and sets of features. So think of it like a Monte Carlo, building up a Monte Carlo test suite.
Yeah.
And then from all those different tests, you can see which one performed the best in terms of the quality for the different features that you selected. So thanks for that. That was a really good question as well. All right, so we were going to talk a little bit more about the AEC part.
Right.
All right.
We didn't quite cover that block,
Yeah.
so let's talk about that one.
Let's dig in. All right, so there's a
So
lot.
what is AEC?
Yeah, good question. Let's start with that. So AEC is short for acoustic echo cancellation. Think about the fact that the smart speaker is playing into a room, and it's creating its own source of music or audio or whatever you're playing, and simultaneously it's trying to listen back to you.
Right.
So that creates sort of a conflict, right? Because you want the smart speaker to listen to you, not to the music that it's playing. So the idea with acoustic echo cancellation is to try to cancel out that playback audio so that the smart speaker is listening to you, not the music that it's playing back.
Okay, so it's some sort of an adaptive filter, basically, that sort of changes its response based on the input that it's hearing.
Yeah, kind of. So it basically has to, the reason that you have to adapt with the acoustic echo cancellation, so think about like if the music weren't playing back into the room,
Right.
then you could basically just invert whatever you're playing out, right? Because you could get a perfect cancellation by subtracting the signal it's playing out from what from the original signal.
Right.
But that's not realistic. Like in the real world, it plays into the room and then it comes back into the microphone input. So that can be thought of as like a filter, right? Because the room is imposing the sound of the room onto the audio. So that's a filter. And so the purpose of the filter that lives inside of this block, the acoustic echo cancellation, is to basically
Nullify.
yeah, well, it needs to learn the sound of the room so that it can nullify the original signal with the room sound included.
Right.
So that's what we call an adaptive filter. And then there's different algorithms for doing that adaptation.
Yeah.
This one's called LMS for at least means squares, but we won't go into the details of the math. But basically, it's learning the sound of the room, so that it can create that accurate filter and then cancel it out when you're playing back the audio.
Actually, here we should probably talk about all these different blocks that you have in the model, right? So you have
Yeah, good point.
Yeah, you have a lot of different blocks. Did you create all these blocks, or did you like pull some of these from the library?
Great question. So I did not create all of these blocks. I didn't even create all of these subsystems. You know, I would kind of view myself as the system designer. Like I put together a lot of these blocks, these components that were created from other engineers within Mathworks, and assembled them all into the smart speaker system.
Yeah.
So some of these low-level blocks are available, you know, in our toolbox products. So let me stop the model for a second.
We can show them, maybe pull up the library browser and then
So there's a couple different ways to find these blocks. So one is you can browse for them. So you can use this library browser feature over here.
Yeah.
And you're going to find a whole set of different toolboxes, we call them, each with their own blocks dedicated for different applications and tasks.
Right.
You know, we're working with a smart speaker, so we can talk in more detail about like audio and DSP are kind of the main components that we would use for a smart speaker. And this LMS filter happens to live kind of in this filtering area.
That makes sense.
Yep, and under adaptive filters, because as we mentioned, like this is a filter that needs to learn the room, so it needs to adapt to the environment that you place the speaker in.
Yeah.
So that's one way to look this up. Another cool feature of Simulink is you can actually right-click on blocks and you can go to libraries that way in case you don't know where it comes from.
Right.
So
Yeah, and then another way would be to just click on the canvas and start typing.
Oh, yeah?
This is,
Yeah.
you know, if you know what block you want, you can sort of just quickly access it that way.
Yeah, so if I like click on this white space, we call that the canvas, and I were to start typing in LMS filter, it's just going to pop right up.
Right.
So that's a great way to build up your models if you kind of know what blocks you're looking for.
Right, and it's going to just save you time. Cool.
All right.
So we talked about AEC.
Yeah, well, let's see if we could actually show the AEC. I don't think we've done that yet. So what I'm going to do to demonstrate it working is I'm going to flip my input path back up to the simulated input path so that we're using the AEC in the simulation. And then I'm going to start the playback audio, and I'm going to increase the volume a little bit. And I'm going to turn off, so this was actually already turned on earlier. I'm going to turn it back off, and then I'm going to basically toggle it on and off, and we'll hear should hear a difference when it's on versus when it's off.
Sure.
Provided I've got it set up correctly. Oops, I think I changed. Yeah, I think I changed my folder. So let's go back into the right folder. That was because I opened up that other example. Let's close that. That should get rid of that error.
Some live troubleshooting here.
Well, it's always good when they're easy to fix.
Yep.
All right, so since I stopped the model, it does, just do its thing and rebuild the first time after you do a stop.
Mm-hmm.
All right, so all of our scopes are going to pop up, and it started playing back in silence. All right, so like I said, we want to see what's happening with our AEC.
Mm-hmm.
So let me go ahead and start the audio playback by flipping the switch over to go again.
And the AEC is disabled right now.
It is disabled right now, yeah.
Right.
All right, so what I'm going to do is right now we're listening back to the audio that's coming out the speaker down here.
Mm-hmm.
I'm going to flip this switch, and what this is going to do is now we're going to be listening back to what the microphone is hearing.
I see. Okay.
So what we should hear is we should still hear a little bit of, let me turn it up a little bit more. We should still hear some guitar sound, but it's going to sound a little bit different because it's going to be going through our room, our virtual room, so to speak.
Yeah. That's the other cool thing about what you just did here is with Simulink.
Go.
Nope. That was
All right, finish your statement and then I'll flip it back over.
You can sort of play around with the model while simulating.
Yeah.
So you changed a bunch of switches so you could change out what inputs you want to play with or look at.
Yeah.
You actually turned up the volume so you can like change the parameters on the go. So you can test out different things while simulating, which is kind of cool.
Yeah,
Yeah.
great point. Yep. Very interactive, very dynamic, makes it easy to debug and tune and demonstrate different things.
Yeah.
So yeah, I jumped the gun a little bit there. You heard the word go come back from the model. That was because that was one of our pre-recorded voice commands coming through. So let me actually, when I first flip the switch up, you'll hear that word again, just so you can hear what that simulated input sounds like.
Go. Go.
All right, and then I flipped it back over to silence. So now the audio that we're hearing, it sounds a little funky. It sounds like almost like it's far away, right? That's because it's playing back into the room, and then the microphones are recording what's playing back into the room.
Mm-hmm.
So let's try turning on that AEC, see if I have it dialed in correctly. Yeah, so when the AEC activates, it cancels out the playback audio.
Yeah.
So I'll turn that off and on one more time. You can hear the difference. It's quite substantial.
Right.
And now the only audio we're hearing is a little bit of background noise that I built in to simulate that like kitchen environment, like you're in a washing machine running in the background, something like that.
Oh, I did see that in the model somewhere, right? You did have like a
Yeah.
washing machine playing.
Yeah. So if you go into, I don't think we showed this block earlier, but if you're going over here, this is a way that you can queue up different WAV files, audio files in Simulink, send them into the switch. And this is where I've got all my different voice commands queued up, and I can select which one based on the switch that's selected.
Mm-hmm.
But I've also got this background noise here that's
Right.
being summed into the model as well, which is like washing machine noise and a little bit of street noise, just to muck it up a little bit and make it more realistic. Because if it's too perfect, you're not really thoroughly testing it if it's too perfect.
Yeah. So did you actually sit in front of the washing machine recording it?
I did not. No, somebody else did, and I copied their files from the internet.
Yeah, someone else did that.
Yeah.
Yep. Cool. So that was the input path.
Yeah, I think we finally covered all of it.
Yeah.
There's a lot in there.
So so I guess to recap, we gave it some sort of a voice input, and then we used machine learning to figure out to predict what was said.
Yep.
Right. So at this point, we just have the word that was predicted. So in this case, it was either go, stop, up, down, or
Yeah,
silence. And then now we move to the output path.
Yeah, let's do that.
Yeah.
All right, so if we come down here to the output, we have these two kind of funky looking blocks down here. We haven't seen blocks that look like this. The reason these look different is because they're actually what we call state flow blocks. So this is kind of an add-on to Simulink that allows you to represent state machines. And the state for this smart speaker is either off or on. So that's a pretty simple state machine. And then there's another one down here for increasing or decreasing the volume. And what's cool about this is it'll actually respond, again, in real time to the different commands that we give it. So why don't we try, let's flip back a couple switches here. I'm going to go back so we're listening to the output. Let's start our speaker back up. Okay, so we hear the audio playing now. What I'll do now is give it some commands to turn the volume up and down, and let's look at our state machine.
Yeah.
Up. Down. Okay, so you could see the highlighted boxes indicated the state machine was responding to the different commands. So when it hears the word up, it goes into an increment volume state. It executes that state, and then it returns back to waiting for another command.
Yeah.
So it's a pretty cool way of visually modeling exactly what's happening in the state machine.
And it actually shows you what state it is in, right?
Yeah.
And it switches between states, and you can actually see it switch between the states.
Yeah, so it makes it super easy to
troubleshoot
and debug. Yep.
Right. So should we talk a little bit about just state machines and what state machines are?
Sure. Feel free.
Right. So the idea is you have a system and it has a particular set of states it can be in, and you want the system to sort of remember, where it was earlier, what the input is, and where it needs to go next. Actually, the documentation page of from Mathworks does a good job of it. So if we go into
where would you like me to go?
The Mathworks doc, and then just search for state machines. It should pop up. Yeah, so that's the state flow documentation page, which is that tool, the tool that sits on top of Simulink, where you can model the states. But if you search for state machines, I believe that should pop up, and there's a really cool page.
State machines, plural maybe?
Maybe.
Model finite state machine?
Yeah, let's try that one.
This looks like a good one.
Yeah. So it just gives you an indication of an event-triggered system. So when you have an external event coming in or a trigger, you can model the actual states that you want your system to be in and respond a certain way for that particular trigger.
Yeah. So it's a super handy tool, because if you imagine trying to debug state machines in code is it can be tricky, because you usually end up with like a lot of switch statements or a lot of if statements, conditionals, and you have to place breakpoints all over. It could be hard to figure out, and here you just kind of see what's happening in real time as it's running.
Right.
Yeah.
Okay. So we had the word, and then based on what that word was, you were picking a state for the system to be in.
Yep.
Right? Okay. And then should we go ahead then?
Yeah, so we can take the output of those state machines, and they basically feed our speaker output processing, right? So if we dig in to this, we can see that our playing signal and our volume signal both come into this next system speaker output processing. So before I dig into that, I see we have another question. Let's take a look at that. How would the model respond if a mic captures the conversation between two people near the microphone? For instance, I'm going up the stairs, follow me there, go sit down. How would you modify your system? That's a cool question.
Yeah,
so,
that's a good question.
Yeah, so the I guess the challenge of this is a problem that's often referred to as a cocktail party problem. I don't know if you've heard of that, Akash, but it's a problem where multiple people are speaking simultaneously, and you're trying to understand just one of them. So it's a common problem that's a lot of people are trying to solve, and there isn't necessarily a simple solution. There's a lot of of different approaches that people take, and I believe we actually do have an example, a speech separation related example in our audio toolbox as well. The short answer is right now this particular model is not doing any of that processing by default, but we could add probably an additional block if we wanted to. in front of the speech command recognition to potentially do that.
Yeah. I'm trying to think, the other way smart speakers just handle that, I guess, common problem which is going to happen is just the use of command words. So it only activates when you say a certain word that it's trained to listen and pick up. And so you sort of use that trigger word or the command word to activate the system, and then you know that person who is talking actually means to talk to that smart speaker. So in this case, I know you've trained it to pick up certain words, but that could be, that's one way smart speakers solve that issue.
Yeah, it's kind of, if I use those words in the context of a sentence, it might not do as good a job as recognizing it as if you're talking to it, So, but it's a good question. It's a good problem. When you start getting into the real world scenarios, this is kind of one of those things where it's easy to make it work pretty well for most scenarios, but there's always going to be difficult edge cases and challenges that you can throw at the device and try to use Simulink and MATLAB as a tool for figuring out how to solve those other challenges. All right, so we're now down here in speaker output processing.
Right.
One more system that we can dig into and see a lot of stuff happening under the hood. So when I started back the playback, you guys heard a guitar playing some music. That's coming from this block right here. And I have the option here, again, I have a switch where I can select whether or not I want to hear that guitar, or I want to use one of these other signals over here. And these are more for like audio measurements and verification. So I've got like chirps and impulses, and I can use those for other tasks, more kind of testing types of tasks.
Yeah.
Keep working our way across.
Right.
We start seeing some other audio kind of related blocks like equalizers, limiters, and things like that. So this is again, just pulling from our catalog of available blocks in the audio toolbox for doing this common sort of audio processing. So I didn't have to write any of these blocks. And what's neat about these guys is, I can, when I look at the individual blocks, they'll usually have an option here so I can kind of see what my response looks like. Right now I'm not using this EQ, but if I were to start applying some gains, I can see the changes in my system as I move around the gains, or I move around the center frequencies for that EQ.
Cool. I guess we should talk about the MATLAB icon.
Very observant.
Right. So Simulink is a platform that you could use, but it is integrated pretty well into MATLAB. So if you had MATLAB code already that you know and you've tested, and you want to import that into Simulink, right? This is the block that does it.
Yeah. Yep. So we call this a MATLAB function block. So it's basically, if I double click on it, it's going to bring me to an editor, and I can see a MATLAB function has been added in here. This is a super simple one. It's basically, I can do it all in one line of code. But sometimes it's just more convenient to do code rather than blocks. It just depends on your preference.
Yeah.
And it's also a really handy tool if you already have a lot of MATLAB code written. You don't have to rewrite it in Simulink blocks. You can just use to get your code in.
Right.
So so what is that block doing in this case? It's actually helping me convert a decibel value to a magnitude value. And the reason I want to do that is so I can set my volume in terms of dB, because that's a pretty common unit that people use when they talk about audio. So my voice command sets a volume in dB, and then I export a dB value from this lookup table, and I feed it into here. That gives me a magnitude, and then I can just set my gain by multiplying my audio signal with my volume level.
Right.
And
So
so
you're setting the volume.
Yep. And then I've got my volume, my signal with the volume applied to it coming out of this of this system.
Yeah. Okay. So we should probably now just look at all the colors that are on the model, because that's the other thing that sort of strikes you.
Yeah, there are a lot of colors here, aren't there?
Yeah, there's a lot of colors on there. So what are those colors, Adam?
Yeah, so right now there's a lot of colors in the model because I'm using one of the visualization features in Simulink that is helpful for informing you what's happening in your model, and the colors represent the sample rates that are happening inside of my model.
Yeah.
So I can actually see what those are if I turn on this thing called the timing legend. And now I've got kind of this is the legend or the key that tells me what sample rates are happening inside of my model.
Yeah.
This is showing me the periods right now. If I want to see the rates, I could click on this. And I can see there's a bunch of them. And the reason that is because I'm dealing with different sample rates of audio. So what ends up happening is I've got audio input. It's fairly common to run microphones at lower sample rates because for speech, a lot of times you don't need to have a higher sample rate. So we're using 16 kilohertz up here. And then for music playback, you kind of want the maximum quality of audio. So we use a higher sample rate down here. We use 44.1. And those sample rates are represented up here in my timing legend.
Right.
And then I also end up with a few more colors even than that because there's the idea of going between the different sample rates. So Simulink provides me really useful tools for doing that.
Right.
Like we call upsampling, increasing the sample rate, downsampling for decreasing.
Yeah.
And what I'm doing is I'm using these to go in between the rates, and Simulink automatically figures out, what is the timing necessary to do that sort of scheduling to go between the different rates.
Yeah.
So that's how I end up with a whole bunch of different colors in my model.
Right. Yeah, that's the cool thing about the Simulink engine is just it takes care of time natively, so you don't have to worry about any of the timing or synchronization. Simulink just does that for you. So in this case, Adam has sort of an interface between the dark blue, which is much faster, and then the light blue, which is much slower signal. And then there's a downsample block in between that sort of does the rate conversion for you. So you don't have to keep track of counters or anything like that. Simulink just does that in the background.
Yeah. And again, this is one of those things where in comparison to hand coding, this is just so much easier because when you start mixing sample rates in hand code, you have to do a lot of kind of manual scheduling to keep track of, okay, now this frame arrives after this many ticks, and this frame goes out if that many ticks, and it can get really messy, and the timing engine in Simulink is really, really helpful for that.
And you did say frames, so we should talk about those numbers there. So the numbers there that you're looking at are actually the signal dimensions, and you can turn that on and off so you can like toggle between them so you don't have to look at it every time, but it's just a good indicator, and it gives you a sense of the data type and the data propagation through your model, which is a really helpful and handy debugging tool when you're modeling and putting together.
So I just leave it on all the time, so that's why I didn't mention it, because sometimes I just forget it's even there, because it's such a helpful thing to just have turned on. I just kind of get used to it.
Yeah.
And it's telling me, the first number is telling me how many samples are coming out per frame. And the second dimension is telling me how many channels, in this case of audio data, I have coming out in each frame.
Right.
So since this is a microphone signal, it's just a mono microphone. It's, it's like on my laptop. So it's 124 by 1. And the 1024 is something that I get to control because I have a parameter here called frame length that I can set inside of my device. And so if I want to lower this, which I might want to do if I want to minimize the latency through my system, I have control over that.
Yeah.
And just as a point of comparison, that's a mono signal. Over here, when we're playing back the audio, we have a stereo signal.
So that's 2 channels.
Yeah, 1024 by 2. So that's the difference.
Okay. Yeah. Yeah. The whole idea of using frames is just model speed up, so simulation speed up. So you process a chunk of data at a time, as opposed to just single samples. So it's much faster. Yeah.
All right, we got another question. What would the response of the system be if Akash and Adam both speak at the same time? Well, I think this is kind of similar to the last question, right? So it's like the response is probably going to vary depending upon which one of us is maybe louder.
Or closer to the microphone.
Yeah, so whichever command is greater in amplitude is probably the one that it's gonna pick up. In this case, I'm the one that's closer, so I think it's going to be.
It's probably going to pick up what you're going to say.
But again, like that would be a good future enhancement opportunities to see if we can improve on that.
Yeah.
and maybe in the next version of this demo.
Okay, so let's quickly talk about the device scopes.
Yeah. So yeah, this whole top right-hand side, from top to bottom, is the section that we're calling audio devices and scopes. So a scope is one of these things, you know, and if I close these, I can always reopen it just by double-clicking on that scope in the model. And I've got the time domain, I've got the spectral domain, and I've also got the device writer, which is the inverse of my microphone, right? So it's playing back the audio that we've all been listening to the whole time.
So maybe let's look at the spectrogram a little bit more.
Yeah, yeah. So we've just been playing it, but there's other cool things we can do with it. Let me make it bigger.
Yeah.
And
so this is the signal and the frequency domain, right?
Yep.
And so what kind of information can we glean from here?
Good question. So let me resume the model playback. So we see we get like this real-time spectral response that we can visualize. So it's just useful, obviously, as a visualization tool to see what's happening in my spectrum. But I can also use it as a measurement tool. So there's a whole bunch of buttons up here. Let me pause the model and just open up a couple of those. So we've got, you know, commonly in audio, one of the things that people like to look at is distortion. You know, just to understand is like maybe you're working on like a smart speaker design. You want to know like at what level does my system begin to distort. So these distortion is basically a measurement of the power of the harmonics relative to the fundamental. So in this case, we're looking at an audio signal, like a musical signal. So I can't really extract that measurement from a musical signal, but I could feed in, you know, if I were doing test and measurement, I would feed in a sine wave or something like that.
Right, yeah. So this is a more complex signal, so you're going to have different frequency components to it. So it's hard to figure out. It's just spread over different frequencies. But if you probably had like a chirp signal or a sine wave, then the frequency becomes aberrant.
You just reminded me.
We have a chirp in that,
we do
right?
have a chirp over here. So I'm going to flip on the chirp. It might be a little louder, sorry. So it's not pleasant to listen to, but now I can visualize that measurement more accurately, right? So like I said, it's the ratio of the harmonic to the fundamental. Let me see if I can pause it. There we go. So the fundamental is obviously our big spike here. And then the harmonics are going to be these little guys that we see over here.
Right, yeah, so the spectrum analyzer block, so that's what you would use when you want to pick out frequency information of the signal. It just does a good job with that. Okay, we have another question in chat.
Oh yeah, we do.
So the question is, can you separate speakers with the Beamformer?
That's a great question. So yes, you can. So right now, the Beamformer is basically in a fixed location. And if I click on it, I can see I've got a set of different angles that I can steer it towards. So that's one of the useful features of beamforming, is to try to focus in on the sound that you care about versus the sound that you don't care about. So in this case, I only have one speaker in my simulation, or excuse me, I have the speech command speaker, and then I have, I'm using speaker in terms of the person speaking in this context, not the playback speaker.
Okay.
So I have the person speaking the voice command,
and then
I
sources.
have then I have another person speaking just some gibberish. So let's see if we could actually hear that. If I steer towards the other speech, let me flip the switch so we hear the input signal, and let me flip this switch so we hear the simulated command. And then let me go ahead and pause it. Whoops, hang on.
So that's the chirp.
Let me turn off that. Why are we still hearing the chirp? We shouldn't be hearing the chirp. Let me see. Okay. Yeah. All right. So we're hearing that background noise. If I let's steer towards the speech command.
Down. Down.
Right. So it's
down.
The actual speech command.
Yeah.
Down.
Which is at 30 degrees.
Down.
Yeah, you can hear actually
down.
When I flip the
Down.
beamformer angle to other speech,
Down.
the clarity
Down.
of the down command
Down.
gets harder to understand.
Down.
So let me go back and forth one more time.
Down. Down.
So
Down.
steer towards the speech command.
Yeah.
Down.
Clear and easy to understand.
Down. Down.
And steered
Yeah.
away, it gets more
Down.
muffled and harder to understand. And that's because
Down.
we're reducing the amplitude of the signal from the
Down.
speech that we care about.
Down.
And I can reduce it even further, I think. If
Down. Down.
well, I guess the noise
Down.
is actually a little bit closer, but
Yeah.
you get
Down.
the idea.
Right. Right. Right.
Down.
Yeah, great question.
Yeah, thank you.
Okay. Yeah. So that I feel like we've covered.
Covered a lot.
Yeah, we covered a lot of
anything
stuff. So that was the model. Again, it's on the documentation page. So if you wanted to look at it and play with it, you can do that. Maybe we should talk about just like next steps and how people can get started a little bit.
Sure.
Right. So a great way to just start out with Simulink, or if you're new to signal processing, would probably be the signal processing on-ramp. Adam can bring that up.
Yeah, we'll just search for MATLAB signal processing on-ramp,
Right.
and you're going to get this cool self-paced tutorial page. This is a great place to get started in MATLAB and signal processing. And then we have another one for Simulink as well, so you can find that also in the same area of the on-ramp section.
Right. So we have, similarly, there's a Simulink on-ramp course that you can get to and go through. And then also just documentation.
Yeah.
I feel like the signal processing toolbox and the DSP system toolbox, the documentation page is so extensive, you can get started and just basically find examples that are closest to what you want to do, and then work off of those.
Yeah, so as we mentioned earlier, this smart speaker lives within our product documentation, so you can find it as an example there.
Yeah.
And like Akash was saying, like there's so many other really cool, useful, real-world type examples within the audio toolbox and the DSP toolbox if you're specifically interested in this particular area.
Yeah.
So I guess we're good.
All right. Yeah. So I don't know if there are any more questions in chat, but that was what we wanted to show you today, and hopefully you've taken away just a little bit more about Simulink, learned a little bit more about MATLAB and signal processing.
And a little bit more about smart speakers.
And smart speakers.
All right,
Great. Thank you, everyone.
thanks.